I really appreciate you guys coming and the opportunity to talk to you. I am not a vehicle person. My background is manufacturing, but it's exciting to be around vehicle people and to learn about what's happening in this space. And so I want to have some of our researchers here with me to help me communicate things that are happening at CAVS. Since I came out of the manufacturing world, one of the most preeminent books that I read early in my career, it was called The Machine That Changed the World. So I don't know who has read that, but it's a seminal book as it relates to lean manufacturing, the Toyota production system, and it gave us a great expose of the different strategies for manufacturing the vehicle, but not just the vehicle, in manufacturing anything. But in the book, it talks about the car being sort of the essential product, right? Even back to Henry Ford's days, where he wanted to have a system of manufacture that allowed people who are working on the line to be able to buy a product, right? And that kind of equity it pervades the whole automotive industry, and we've seen enormous improvements in things. So as we were looking at the manufacturing challenge that's out there, there's an area of a Toyota production system that they talk about. It's automation with a human touch. And every time I hear the autonomous vehicle talks, I think about that. It's automation with a human touch. And no matter where you're at in this thing, the human's part of it, right? The human is the essential part of mobility, and the part that we're focusing on anyway. Just a little bit about we talked about the meal. Of course, this is a recent picture, but I want to dive a little bit deeper into the history of the meal and how these things connect. So this is some pictures around 1920s. And if you can see what this operation here involved was bringing in cotton, which was a staple crop in our area. Supply chain was very local. And so in the mill, you had production of yarn, looms for fabric, okay? And it was a very high volume plant, particularly in into the 1940s and 1950s. About the same time, this building started in 1900, and this is pictures of 1920. About the same time in Japan, the founder of Toyota dealt with automated looms and dealing with much of the same challenges that happen here in this building. So it's very fascinating. The first automatic loom by Mr. Toyota is pictured here, and he developed it about 1924. And it was the first illustration of automation with a human touch. In fact, this in the Toyota production system, it's called Jidoka. Now, I will not embarrass myself for all of our Japanese people here, but it's very important, meaning ultimately this involves two different phrases. One is automatic, and the other is autonomous. And so the achieving of Jidoka has to do with a topic called autonomation, which is the characteristic that machine has, autonomation. And it doesn't mean stopping automation. It means this combining of automatic and autonomy together. And one of the wonderful aspects that was revolutionary for this loom in the 1924 was that it could self-regulate, and it could see where there's a problem in the looming operation, and it would stop it immediately when there's a problem and it has to be fixed. And ultimately, what they're allowed to do is freed up a person from a machine to a person managing machines. It relieves the worker of the need to continuously judge whether the operation is normal or whether or not an abnormality exists and we need to pay attention to it. And so this is the concept of Jidoka that has revolutionized a lot of manufacturing. And I think there's actually a connection here to the autonomous driving. When we think about autonomous driving, we've already talked about there's various levels of autonomy, from level 0 to level 5. And you can see level 5 is full self-driving under all conditions. Just a step below that is self-driving under certain conditions. Step 3 is limited self-driving, but then have some times where the operator takes control. And you kind of back it off to occasional self-driving, to driver assistance, to no automation. And so with these 5 levels of vehicle autonomy, it really looks like sort of level 3 is where, if you kind of think of the equipment, the loom as being the machine, the vehicle being the machine. It feels like in 1924, Mr. Toyota really kind of discovered this principle of an intelligent machine and how it would impact the human. And so this is that notion of automation, I think maybe about maybe level 2, level 3 in this hierarchy of autonomous driving. So he was working this problem at the same time that this building was under production, and I'm sure they were dealing with many of the same challenges that he actually solved. 2017, last summer, my first experience, and really only experience in autonomous driving, was at this location in Strasbourg. It was the event was a international smart transportation conference in Europe, and it was the first day, they advertised as the first day that someone would ride in an autonomous vehicle across national borders. So I don't know if it really was, but that's what I was told. So I wasn't on the first ride, but I was in the first day, and so I was this is the car. It was developed with Vedicom, which is a French public-private partnership. And so I was very, very excited. I was in the back seat of that car, and we went from Strasbourg, France, Strasbourg, Germany, and back again. So we did a legal U-turn after we crossed the Rhine River. So that was my first experience. It was very interesting. In fact, I have a short little video. And so that's me in the back seat trying to take a picture of the autonomous car, and we were merging into traffic. It was very, very thrilling, and in fact, some lessons learned from this event. For one, there was an abnormal condition occurred, and it was, who would have ever thought? If you look at this, we were following this other vehicle, and you look at the top yellow circle over there, and the yellow vehicle was filming us, okay? They were filming us, and so we were fairly close to that yellow vehicle, and we were trying to get good pictures and such. But guess what? The interior of that vehicle was all black, all black. And as we got closer, I believe the sensors were perhaps captured by this all black, and all of a sudden, we're getting a little closer, and Autonomation happened, and you see the red button. So we had to hit the red button. And I was very glad that we hit the red button, because I was thinking, well, wow, we're fixing to hit them. That would be terrible. But after that one event, I was in the car for 15 minutes. It was not worrisome, no anxiousness. It was very, very natural. But I spent most of the time trying to make sure my phone was working so that I could capture this episode on my video. And of course, you know how that is. On the phone, you want to get something important, and then all of a sudden your phone is full of no memory space. So I had to delete pictures of weddings and birthday parties and things like that. I was all worried about the phone, but not the car. But it was a great experience. So I guess I experienced distracted rider syndrome. But it was a great experience in my first experience there. And just very quickly, just from a standpoint of manufacturing, which is a much more controlled environment than the driving, but we have seen tremendous improvements in automation and collaborative robots and human-machine interfaces in manufacturing. But I can say for 30 to 40 years of intense work in manufacturing, this level 5 automation is very, very difficult. Level 5 autonomy is very difficult to achieve, even in a highly controlled environment. In fact, I believe it was McKinsey just did a report on manufacturing tasks and looking at how many of them could be automated over the next several years. And I believe it was by like 2035, something like that, somewhere between 25 and 60% of manufacturing tasks could be automated. Again, the error bar was very high. We don't know where technology is going. But it's a very challenging task, as Stanford mentioned earlier. And the other thing for manufacturing, you get a lot of quick wins early. But it's the last 10 or 20% of automation that's really, really hard. And perhaps we'll see that in the vehicle as well. And then from a manufacturing standpoint we should always look at the machine serving the person, not the person serving the machine, right? And that actually gets to the heart of our conference is when the equipment serves humans' needs, then it has a lot of value for us. In fact, there's a nice comment about Toyota. Toyota's culture places humans and not machines at the center of the company. And so that's important. So I believe that this notion of automation with a human touch is very, very important to us. So I wanted to briefly talk about some of the activities we have, investments we have going on at the university and at CAVS, and I have our team here to help us do that. We have a couple of selected projects. One is a pedestrian-vehicle interaction using virtual reality. We also have a Halo car project, which is an autonomous vehicle that we're developing from our researchers and students to be a test site for us, a test vehicle for us. And then we have a test track where we are in the middle of developing. And then we have what we call the MAVS system, which is our Mississippi State University's autonomous vehicle simulation world. Then we just recently completed an industrial material handling autonomous project that we're very, very proud of the team that executed that project very well. But because of confidentiality, we can't talk about that very much. But it's an autonomous vehicle within an airport environment, in a material handling environment that had different kinds of loads, and it had particular interesting challenges. So with that, I'm going to turn over the conversation to Dr. Carruth, and he will talk to us about the pedestrian-vehicle interaction project.
All right, thanks, Clay. So we have a slide here on some work that we've been doing for the last couple of years, and in fact, some of this was initiated as part of our relationship with Nihon University and has grown since then. This on screen, you can see an image of we're using HTC Vive and Oculus Rift technology to put people inside of our simulation environments. And what we're looking at in here in particular is in this image is we have one of our students walking across, and we have the autonomous vehicle attempting to communicate to the pedestrian that it is safe to cross. And so when we look at autonomous vehicles interacting with pedestrians and bicyclists and other vulnerable road users, there's a discourse that happens between a human driver and those pedestrians. Part of it is that we just know what each other is most likely to do. We assume that a driver doesn't want to run over us when we're in a pedestrian. The drivers assume that the pedestrian is going to generally follow the rules of the road. But we're always aware that there is a possibility that someone's going to come out into traffic, and we're aware of those possibilities. So that work that Stanford was talking about, trying to interpret a pedestrian's intent. But in addition to that, our pedestrians are trying to interpret the intent of an autonomous vehicle. And in fact, so Dr. Suchi Dev is a postdoc at CAVS and is one of our moderators over the next 2 days for the Roundtable. This is some of the work that's been guided by her, where we want to know how to potentially do pedestrians misinterpret those messages. So if I have a rider in an autonomous vehicle and the rider is looking down at their tablet because they're not in control, or they're messing with their phone, like Clay was, deleting files, while the autonomous vehicle is coming up, a pedestrian that's looking at them may interpret the fact that the driver is heads down as the driver's not paying attention and it's not safe to cross, when in fact it's an autonomous vehicle and it is signaling to them that it is safe to cross. So there are some very interesting issues when we talk about how will someone interpret what is the behavior of the autonomous vehicle, and is it safe for me to cross, or do I need to wait for it to continue? There's an argument that maybe an autonomous vehicle will always stop, and in our industrial settings, our AGVs are often programmed that way, that if a worker steps out into the aisle, the AGV will stop. But when we talk about vehicles on the road, then we are concerned about the bad behaviors of pedestrians or other vehicles. We cannot have vehicles that just automatically stop for everything that comes out in the road. We have to have some balance, and we have to have also communication to someone that's crossing that the time where it is safe to cross is coming to an end. Now, we use the VR environment to let us do that kind of research because, one, it's impractical for us to do in the real world for several reasons. One is safety. It's a lot safer to have someone walk across the street inside of our simulation. Two is that, like say for example, I can do a lot more conditions inside of the simulation than I can in the real world. We can test literally hundreds of different methods of communication inside the VR in the same time and cost that it would take us to test just 2 or 3 in the real world. And then also in terms of time, when we go out to do real world data collections of pedestrians crossing the street with vehicles, the logistics of that are just astonishing. And so trying to schedule and take over a road and do the kind of scheduling to be able to look at that is very difficult. Inside of our VR environment, we were actually able to collect 60 interactions between an individual and an autonomous vehicle in under an hour. And so by using the simulation with a person in the loop, we're actually able to get a lot more data on how people interact with those systems than we're able to get in the real world. So, all right. All right, Matt.
So I'm going to tell you about our HALO project. CAVS is involved in an internally sponsored project called the HALO project. The name comes from the fact that many automotive manufacturers have what they call their HALO vehicle, and it is usually their most technologically advanced vehicle with a lot of consumer appeal, and in terms of brand, it sits at the very top of their brand, and that vehicle has a residual effect on every other, even the cheaper cars that brand makes, so it's called their HALO vehicle. It sort of sits at the top of their brand and elevates the entire brand. MSU achieved this effect to a degree with a project called the Car of the Future, which you can see in the parking lot. It's just outside, so maybe during one of our breaks you can step out and see that vehicle. And when we decided to launch a follow-up project on a vehicle that would be that would heavily emphasize autonomous technology, we decided, well, why don't we just call this really what it is for the university? We'll call it the HALO project. So that's where the name comes from. And this is a vehicle that pulls together all of the different research that we do at CAVS, and the different groups, different researchers, electrical engineers, mechanical engineers, human factors, powertrain, material science, and give each of these researchers a platform that we can showcase the best that Mississippi State and CAVS has to offer on a single platform. So we're building a vehicle that is autonomous, it's all electric, it's all-wheel drive, and it's intended for off-road use. We talked earlier a little bit about the different wheres of autonomous vehicles, right? So we saw the vehicles can be used on-road, and as Sanford pointed out, you know, today's autonomous vehicles are mainly built to recognize existing infrastructure markings, lane markings, signage. Essentially, they're built to replicate what we do when we drive by reading the existing infrastructure. So what happens if you put a vehicle in a completely non-infrastructure environment, just a clean slate, right? So it's almost a completely different paradigm in terms of how that vehicle has to be built to operate. So that's the challenge that we're taking on with our HALO project. Some of the sensors that we're using on the vehicle include 6 cameras, front, rear, and side, and 3 LiDARs, and altogether this gives us a full environmental awareness of the vehicle. We will add radar at some point, but that's not on the vehicle currently. We're doing some interesting things with the way we're mounting sensors to try to, as we fuse the data, get a more focused and accurate view of the world in the areas of the vehicle that we're really most interested in it, particularly right in front. And this is where we're also using the NVIDIA Drive PX2 GPU supercomputer. Now, as we fuse all of this data together, it becomes really interesting because Sanford showed an image of a free space map. It was on a mostly flat road, and so there was the purple area in the middle. That's the free space that's safe to drive. That's a common algorithm. But what if the space in front of the vehicle is not flat? What if it's not planar at all? It's maybe quite bumpy or hilly or angled. What if instead of doing neural net object classification for cars, pedestrians, and motorcycles, it's trees, logs, and deer? Now the deer one has actually been addressed somewhat in industry, but recognizing trees and logs and rocks in general has been less focused on than the on-road object detection and classification. So that is where we feel we can really make an impact in the autonomous vehicle industry. We're collecting data in off-road environments. We've already taken this vehicle platform out and collected some data. Clay is going to talk to you in a minute about a really neat facility that we're developing in order to help collect that data. And we take that data and we fuse it together, and we're working on really novel ways to process it and look at the world model, which we then uses to control the vehicle's actions. For instance, we're working on what we call a characterized occupancy grid. So we'll take all the data from all the sensors, fuse it together, put together everything we know about the environment, and say if this room is our environment, create a 3-dimensional grid around the entire room, and in each grid we say, inside this cell, what is inside the cell? Is it unoccupied? Is it occupied? If it's occupied, what do we know about what's in it? What are the characteristics of that cell? What's its tangency or adjacency to the cell next to it? Is it a step or is it a smooth curve? So that represents something we can drive over. So we have to classify not just obstacles, but objects, and objects can be either traversable or non-traversable. So these are all of the many kind of unique challenges that you started to get into when you're in a completely unstructured environment, such as an off-road environment. So we're really excited about this. Briefly, I mentioned the vehicle is all electric. We have a 90 kilowatt-hour battery pack, which is good for about 230 miles of range. If you're familiar, just to put this in perspective, the longest range Tesla vehicle has a 100 kilowatt-hour battery pack, so we're on par with that in terms of range. The vehicle is driven entirely by electric motors. It has one for each wheel. Altogether, it makes about 10,000 Newton meters of wheel torque. To put that in perspective, each motor has about the same wheel torque as a Mustang GT, and we have one on each wheel. So the powertrain of the vehicle will be very high performance. And MSU isn't doing this alone. We have 6 industry partners that have come on board and provided either cash, in-kind donations, or and/or engineering support. So we've built almost a consortium of industry partners that are helping us achieve this, NVIDIA being one, and also 5 other partners. So this vehicle is back in our shop right now, in our lab, being put together with quite a large team of researchers working on it, putting it together. So we're really excited about this project.
So one of the things that we want to talk about with you is we have just acquired 50 acres that are close to our building. If you look at this, an aerial shot on the right-hand side, the CAVS building is on the far side over there. Then our high-performance computing collaboratory is over there, and then we have 50 acres behind. And so we are converting this to an autonomous vehicle test track with a large focus around off-road. And so you see we're going to have different artifacts where we're sand, wooded trails, hilly terrain. We'll also have a concrete pad. So this is the vision that we have. Right now we've acquired the 50 acres. So we have a 50-acre wood. And the first phase will be looking at looking at the off-road situation. We have some sponsored research with the Army and other people who are interested in that. But we want to go beyond that and look at other aspects. It could be, Professor Snyder and I talked about precision agriculture and autonomous vehicles in the agricultural environment. So there could be some nice collaboration opportunities. We look forward to discussing that. And so the vehicle on the far left is an early vehicle from the Army that we did, and we developed a test plan around autonomous vehicle to determine how well it performed in a variety of off-road environments. So that completed just a month or two ago. So with that, I'm going to have Dr. Chris Gooden come talk about a new system that we are calling MAVS. Yep.
All right, thank you. Yes, I'm Chris Gooden, and so real briefly, I want to talk about MAVS. Have until when? We're already over. I'll make it quick. Like Dr. Walden said, it's the MSU Autonomous Vehicle Simulator. And basically the goal for the simulator is to provide a simulated test area that corresponds to the real test area, to the wooded test track that you see here. And so, fortunately, we got a great motivation for why we want to use simulation in general in the last talk. But what I want to talk about the MAVS is our focus on off-road. So there's some unique problems in off-road. And the biggest one being that one of the primary sensors that you are going to use, obviously, is LiDAR. And there's some real problems with LiDAR interacting with vegetation. Before I came to Mississippi State, I worked for the Army for 9 years. And I once heard an angry colonel say, "I'm tired of seeing my 20,000-pound trucks get stopped by a blade of grass." Okay, but that's what you see when you try to use LiDAR for autonomous navigation in vegetation, because the LiDAR can appear, the vegetation can appear opaque to that particular sensor. So certainly multi-sensor approach is necessary, but from our simulation environment, we knew that we had to get the physics of that sensor vegetation interaction correct, and it extends even beyond vegetation to things like the soil, right? So we can't assume that every surface is drivable when you're in an off-road environment. Just because it's flat doesn't necessarily mean you want to drive on it. And if you've driven around here off-road very much, or further south where I'm from in Vicksburg on the Clay, you may have found that out the hard way. Getting into a little bit of the details of it, I won't talk about this too much, but the simulation environment is built around MPI, and that's so that we can scale it up to multiple vehicles, really complex environments, really complex simulations of the vehicle dynamics itself on the supercomputer. Again, we got a great background on why we want to use simulation for autonomy in the earlier talk. It's funny, we brought up the deer. That's another one that if you drive much around here, you understand. That's not just a joke. If you drive here in Mississippi very long, you're going to hit a deer. It just happens. So it's one of those things our simulator also has to do. So I've kind of touched on this, but there's unique challenges associated with off-road, another one being dust. And so the MAVS is being programmed with the physics necessary to address the sensor interactions with those environmental factors in that perception phase, so that the other phases of the simulation basically will be correct. A fairly recent use case. So Matt talked about the Halo vehicle and the unique things that they were doing with the LiDAR sensors on that vehicle. we used the MAVS recently to do a study of the best way to orient. There's two sensors on the front of the vehicle that are scanning, three-dimensional scanning LiDAR sensors, the Quanergy M8 sensor. And they're tilted forward like this so that the scan pattern sort of weaves right in front of the vehicle and gives you a very dense cloud of points right on the ground in your projected area of travel. And so we did a simulated study with finding the optimal tilt orientation of those sensors to give you the maximum coverage at different zones of distance. And you can think about those zones of distance corresponding basically to speed that you can travel. And you see some of those scans on the lower left-hand corner here of your screen. And what we were able to find is that basically a very high degree of rotation, 87 degrees of rotation, gave us the optimal coverage on the ground for detecting obstacles. And the neat thing, of course, about using simulation is we basically did this from the comfort of our offices in an afternoon, whereas the similar study would have been a lot more complex. So the current status of MAVS, really just started development of this in December. So this is very early on, but we're already, as I mentioned in this previous study, we're already being able to achieve some of the goals of assisting autonomy developers in creating a better product without having to go do a bunch of field tests, and steadily incorporating the environmental physics for vegetation and dust and off-road driving.